Hi everybody, welcome. A quick introduction to me. I'm currently the Director of Engineering at Raven Controls. I've spent most of my career working as an early hire at startups. And the reason I've done that is I'm passionate about taking an idea from scratch and turning it into an amazing product. I've been lucky to work on some brilliant projects over the years. I first started working with PHP over 20 years ago when I was about 14. And I'm about to turn 39, so pushing 25 years. I think PHP was about version 3 at the time. Can't really remember, it was a long time ago. So it was a dial-up era. The internet was very much in its infancy, and I'd learned some HTML, and I wanted to write a hit counter that counted the number of visitors from a band's website. That was a popular thing at the time. And I spent countless hours working with SP Classic and Perl, and it didn't go so well. So enter PHP, and it just worked. I solved my problem, and I've been working with it on and off ever since. Bring this to today, where we've got all these amazing tooling and ecosystem like Symfony and API platform. Back then, we didn't even have classes. So Raven Controls, who are we? We are a startup delivering mission-critical event and crisis management software. Our software has been deployed at some of the world's biggest events, including UEFA Euro 2020 and COP26. In music, we work with some of the biggest arena groups in Europe. And in sports, we work with football clubs from across the English Premiership, and internationally, we've worked with teams from across Major League Soccer and Major League Baseball. And we were fairly early adopters of Mercure, making it part of our infrastructure back in 2018, which is why I'm here. Now, early adoption of technology is pretty unusual for me. I'm usually a member of the Boring Technology Club, so I'm sure some people in this room will have heard of it. But if you haven't, it's the philosophy of using tried and tested tools, because they're well understood, and whenever they're bad, you at least know why they're bad, and the myriad of ways they might let you down are well documented. New technology, on the other hand, brings a steeper learning curve and more unknowns. It's going to let you down, but you don't know why yet. It also comes with the promise of a new way of solving your problems, and it keeps developers happy, because let's face it, developers love playing with new cool stuff. So when we adopted Mercure, I believe it was 0.8, and last week we just saw 0.14 released. So we're still not even at version 1 yet. So for me this was a change, but I was attracted to Mercure, having seen the other innovative work done on API platform, and the integrations with Symfony, and many reasons that we'll come to. So, let's talk. We're going to do a quick intro to Mercure, what it is, why you might want to use it, how Mercure has changed and fits into our system architecture, some common use cases where we'll show how we've utilised Mercure, some of Mercure's key features that I think really sets it apart, tips for running Mercure in production. We've made the mistakes, so you don't have to. And mostly during this talk, I'll be reiterating points that you've already read on the slides behind me. Just kidding. So why Mercure? Mercure is open, both a protocol and an open source hub that implements the protocol. Anyone can create their own hub that implements the protocol or modify the existing open source hub to suit their own needs. It's batteries included, so Mercure takes care of authentication, automatic reconnection, PubSub, fetch and missed events, and more out of the box. It works through server-sent events, which is a persistent HTTP connection, allowing you to stream to web browsers, mobile devices, and so on through native functionality. You don't need any additional libraries or SDKs. And obviously, it has integrations with Symfony and API platform, where it comes included. Getting going is relatively straightforward. If you're already running containers, there's a pre-built Docker image for Open Source Hub. If not, there's a binary that you can install. Both of these just need a handful of environment variables passed in at runtime. Just add the Mercure component to your Symfony app via Composer, and off you go. You can publish updates to the hub in a couple of lines of code. Receiving a message in the browser is equally as straightforward. The event source and URL class is shown, or browser APIs. So like I said, there's no need to install any libraries. And again, it's just a few lines of code. Less than 15 in total across the back end and front end. And that's it. Now you're operating in real time. So now we know how Mercure works. Let's take a step back. So in an early MVP, we used polling to keep things up to date. We polled every 10 seconds and did 6 polls per minute for every single client who was listening. You can imagine that was a lot of traffic. In fact, when we analysed it, it accounted for over 50% of our traffic. And that model wasn't great. So 10 seconds is too long to wait for the kind of events our system's designed to handle. So enter Mercure. I've always taken a lean approach to building software, building the simplest possible version of a feature or a system that meets the criteria, and then iterating on that implementation to improve it. You don't want to spend loads of time on something till you know it's going to be useful. And so that's what we did when adopting Mercure. Took a very simple approach to sending events. We sent the event name, which could be issue created or task completed, and then we would pull a fresh copy of the view or data from our endpoints in response to the event name. So now we had a better approach. We got rid of polling, and we only fetched data from the server on demand. And that approach worked great, but it couldn't last. So this model can hit a hitch when introduced to any sort of scale. When you've got 1,000 clients listening for the same event, prompting them all to send a GET request to your application simultaneously is not the best idea. And when you have a lot of events being created quickly due to the scale, and this process of prompting all your users starts getting repeated over and over, things get slow. And when they get slow, people start hitting refresh. And now you've got more requests to deal with. That's right. You've made your own distributed denial of service attack. And you didn't even have to go on the dark web. Quick disclaimer, this scenario is entirely theoretical. Been reminded to tell everybody that this absolutely did not happen to us. So we iterated on our approach and decided to push all the required data over the wire. So pushing pure data objects, like you do for the features that come with the API platform, for example, works great with single-page applications or mobile apps built on React Native and similar technologies, where you just need to update your state and the view re-renders. And this approach we took for our own mobile app built with React Native. But, and I might be about to get booed out of the room here, because it's an API platform conference, so most of the views for a web app are server-side rendered using Twig. So there was some debate around whether pushing pure data was the right approach, and ultimately we decided the answer was no. It adds a lot of complexity to use JavaScript to pick out numerous elements and update them one by one. So we opted for a different approach. And that approach was pushing rendered HTML over the wire. So if you use a templating system like Twig, you've already got the mechanisms in your back end for rendering individual components that make up your view. So why not reuse those? Make the rendered content part of your server-sent events payload. So pushing rendered HTML with Mercure and patching it in the page, it sort of gives you the experience of a single page application, but with none of the associated costs. I've just shown a simple example where the content is prepended to a target. In reality, you might want to carry out several other actions. So by adding an action and a target to your payload and have a bit of JavaScript on the front end to carry out the appropriate action on the target you'd specified, you can pretty much do any operation. So for an example, in a chat application, You might want to append content to the bottom of a container, or you might want to just replace the entire content of an element with the next step in the process, or remove some content that you've archived. We rolled our own implementation of this, but if you've got a server-side rendered app you want to modernize, and you're thinking about adopting this pattern, the good news is you don't have to. So we started doing this after the same approach was brought mainstream by Ruby on Rails, and it's actually just been recently adopted into Symfony UX as part of the Turbo component. And the new feature is called Turbo Streams, and it does exactly what I've just described using Mercure. And again, it was created by Kevin. The man just keeps on giving. So now you've got two great choices, no matter how you've built your application. If you've got a single page application or mobile app backed by API platform, you can enable the real-time features. And if you've got a server-side rendered app, you can leverage the streams functionality from Symfony UX, which is amazing, really. So whatever your needs, you can get rich sort of real-time features out of the box for your project. Overall, changing to a push model, we more than halved the traffic we have to handle, which translates into a cost saving on compute power, frees up our apps to respond to traffic faster. So costs go down, response times go down. Real wins. So let's take a look at some of the use cases where you can benefit. Most applications will have an area where they have a collection of results, be it blog posts, a list of users, items for sale in a shop, and so on. Now we can get the new items added to our collections in real time. A new item is added and we see it instantly. Whenever a command, handler, or service successfully persists a new item, we emit an event that implements a publishable event interface, and that events handler will push the new content over the wire. And that isn't just cool UX. So the real game changer for us is those seconds spent waiting polling. It's too long to wait for critical incidents. Under the old model, it could add up to 30 seconds of latency for this new issue to pass through the chain of command and issue a response with polling. If we have an issue like the one we've just patched into review arrive, that's not going to cut it. In an evacuation situation, that would amount to a lot more people off-site 30 seconds sooner. Other candidates for being updated in real time are your classic notification icons. We have ones relating to SMS received from the public, a user's tasks that have been assigned to them, and just a general bell containing all other kind of notifications. Using our framework, we can prepend the new notifications onto the list. We can replace the icon itself with one containing an updated number of notifications. Almost every app has probably got cases like this, where something's happened on an area of the site different to the one the user's currently on, and we want to alert their user and direct their attention there. Chat. In any messaging application, you need to see replies instantly. A reply comes in, and there it is. In our case, we receive SMS from members of the public directly into our app, but whether you're working with WhatsApp, other social channels, or your own implementation, you can't have users refreshing to discover whether there's a response. Now, you might be wondering how you can implement a two-way chat when you can only receive messages via server-sent events. And the answer looks a bit like this. So messages are sent by HTTP post and received over server-sent events. And this is actually how some commercial offerings like Pusher work. So it's a service you might be aware of if you've worked with Laravel. The reason it works like this is that you don't want to, if you do want to persist the messages to a database, for example, then you'd be asking your hub or communication server to implement sort of business logic that doesn't concern it. So the nature of server-sent events isn't a constraint in this scenario. It's actually the optimal way of doing things for this use case. And if you're leveraging HTTP2 and sending a lot of messages to your hub concurrently, you can do this with little penalty, as there's no need to establish a new connection each time. Collaborative editing is another application. So we've got two or more users simultaneously editing the same entity or document, where they would be unaware of each other's changes, creating race conditions, overwrite each other, so on. So by posting updates to our server as the user types, we can push the updated content to other users and even disable fields they're working on, so we don't get any unwanted edits. Dashboard and stats provide all of us with an overview of what's happening in our systems. We want to see the most up-to-date data so we know exactly what's going on. We want to have the ability to analyze trends and to identify problems and opportunities as they happen. We want to know nothing is going to interrupt our event or conference. Live mapping. So as issues are entered into the system, given they've got a location on the map, then we can display that location in real time on the map, showing new issues as they occur, and giving an overview of where issues are occurring and identifying problem areas by visualizing clusters of issues. So we've used our clients' own maps of their floor plans and arenas, but you could just as easily feed that into Google Maps or Mapbox, whatever it is you might use, and everybody will be familiar with tracking their driver on an Uber or a delivery, and those apps utilize these real-time updates in the same way. Finally, that hit counter for your band's website. These are just some of the common ways real-time can be utilized. So the possibilities go on, and you've probably got your own ideas how it can be utilized in your own applications. So gather and missed events. For me, this is one of Mercure and server-sent events killer features, and one of the features that go beyond real-time, referencing the title of this talk. Being able to gather missed events is incredibly powerful. It lets us reach into the past and lets us refresh our apps without sending a request for an update. For any app on a mobile device, it means when it wakes up, you no longer have to pull your APIs, pull down a fresh set of data. And in many cases, that data might not even have changed. It's wasted bandwidth and compute power, but when the data has, you're now going to have the exact data you need available to you immediately. So for our use case, this is really powerful. Stadiums and arenas are huge concrete structures with thick walls, and they're often built in the outskirts of cities, and one or more of these properties leads to poor connectivity. Even when apps are in the foreground and listening for events, they can be subject to weaker lost signal. And in this scenario, without this feature, it wouldn't always be obvious when an event had been missed, and as we discussed earlier, this could be critical for safety. In this example of showing how you might track the last event ID in a single page app using the browser's local storage, should be great for visits, between visits to a site. Server-sent events has this functionality that passes the last event ID baked in when your connection drops. So the automatic connection combined with gather and missed events really comes into its own here when you're working in environments with poor connectivity. I think the last event ID also sort of fits nicely with some of the problems GraphQL was designed to solve, like overfetching and underfetching of data, allowing you to make sort of requests for exact data you need. I think the last event ID solves this in a much cleaner way. So it turns your hub into a mini event sourcing system. And the advantage is that the data gets pushed to you. Another key feature is the ability to receive live updates on subscription events. So by subscribing to topics that include the addition of a subscription path and the topic you want to monitor, you can receive a notification when a subscriber becomes active and subsequently becomes inactive. The format can be a little bit hard to grok at first. The Presence API, on the other hand, lets you make an HTTP request to the hub on demand in order to retrieve subscription data. So it lets you retrieve a full collection of all your subscriptions. You can also go into the subscriptions on a specific topic, and you can even check if a specific subscriber is active on a given topic. So to enable these features, you need to set the subscription directive to 1 in your environment variables to activate it. So one use case for this is tracking how many users are online. And if you wanted to, you could drill into which individual users are online. On our dashboard, we utilize this to display how many users are online working at a particular event by capturing subscriptions to topics related to those events. You could take this a step further and capture users subscribing to a topic that relates to their unique user ID in order to see who's specifically online at a given time. So a chat app like Slack would be a good example of this, where it displays or removes a green dot to indicate a user is currently active. So set a value using the size variable to limit the number of messages you want to retain in your message history. By default, this is set to 0, which will cause your hub to retain the entire message history. BoltDB, the default transport, will also attempt to keep your entire message history in memory, or as much of it as it can. So I think you know where this is going. If you don't limit your message history, you run the risk of the hub running out of memory and your hub could fall over. Now, I'm exaggerating slightly, as BoltDB will automatically free memory to other processes, but now we're getting in the realms of input-output operations to disk, which are much slower than in-memory operations. Slowness leads to back pressure on services that are calling, so choose a number of events that make sense for your use case. And once again, this absolutely did not happen to us. So while we're on the topic of message history, you've got a choice of 2 transports in Mercure. So transports are like a queue that links between the process that receives your update from the server and the one that pushes it onto subscribers. They store the message history, and if you're running in cluster mode, allow for the fan out of messages to your multiple hubs. So BoltDB is the default. The other choice is to use the in-memory transport, represented by the local URL. This is the fastest transport because it doesn't retain your message history. It just passes the message for a data structure in RAM and discards it when it's finished with it. So if you don't need your message history for your use case and you've got a need for speed because you've got a high throughput of messages, then this is the transport for you. So we just spoke about the hub potentially falling over. Whether you're calling out to Mercure Hub, anything that requires a network call to another service, maybe Mailgun, Twilio, whatever it is you're using, I like to process those calls asynchronously by making that call on a worker copy of my app or API, utilizing a message queue and Symfony Messenger. I don't want those calls being made from the same copy of app or API that is answering requests from clients. So async event interface in this example is just an empty PHP interface. No methods in it. It's just a marker for routing purposes. If any service you're calling out becomes unhealthy, requests will start building your own app, slowing down your own responses, and eventually, with enough back pressure, your service will become unhealthy. Funnily enough, this is another thing that didn't happen to us. So here's a shot of what our architecture actually looks like. Client-facing apps or APIs offload async events to a message queue so they can respond to clients as quickly as possible. Symfony Messenger pulls messages from the queue and routes them to the appropriate handler inside a worker copy of the app. That worker copy of the app then calls out to Mercure, which in turn pushes the update out to clients. While we're talking about architecture, it's probably worth mentioning how much resources we allocate to our hubs. So we run on AWS, and we assign our containers 2 virtual CPUs, which is equivalent of 2 cores of a processor and 2 gigabytes of RAM. That seems to be ample for us, but bear in mind the size of your messages and how many you want to store in your message history when you're deciding. I should point out, so if you dispatch an update in Symfony via message bus rather than directly publishing it, then it will automatically go asynchronously. So if you configure the message queue already, you remember in the earlier example, we were injecting the hub interface instead of the message bus interface. However, for us, we wanted to offload our events to our workers earlier, so that the time spent doing stuff like rendering HTML or any other actions that are considered secondary in responding to a client, they also happen asynchronously. And that helps us keep response times in our apps and APIs as fast as possible. If for some reason you can't use cookies to pass the JWT that authorizes your clients to subscribe to updates, or your corporate overlords are still dictating you have to support Internet Explorer 7, then the event source polyfill library is your friend. It allows you to pass the JWT as a bearer token in the header of the request, and that's something that's not supported by the official event source implementation. It doesn't allow the modification of headers. And it provides event source functionality where it's otherwise not supported in old browsers that existed before the event source API did. On mobile, so Swift and Kotlin, we've got native event source implementations for iOS and Android. If you're using tech like React Native or another abstraction over the main mobile platforms, then you will need to install another polyfill. So there's a JavaScript implementation based on the browser polyfill I just highlighted, and there's also a TypeScript version if that's what you're using. So these all query the hub every 500 milliseconds with the last event ID. So they're not a true stream, but you can configure the timing to suit your needs there. There was an attempt at a native bridge that seems to have been abandoned several years ago. So I think there's a gap there for a library to solve that problem. That's something anybody's into. So next few slides are all about connections. Use a single connection and subscribe to as many topics as you like on that single connection. Add an event name in your payload or some differentiator so you can distinguish which topic you received the event from and handle it appropriately. Most of the mainstream browsers have an arbitrary limit on the number of connections they can handle from an event source, and in older ones that can be as low as 6 across all your open tabs and windows. So use connections conservatively. More connections also mean more resources used on your server or your hubs running. So if you're running at any kind of scale, it just makes sense. Gracefully close your connections. So if you abruptly close a browser tab or window without closing the connection, you're going to get lots of errors and body stream type errors in your browser console. And if you're using an application monitoring system, it's going to clog it up. You've got a system like Sentry or something similar, you want to focus on actual errors and you don't want to burn through your ingestion allowance. So capture the before unload event and close the connection then. In a single page application, if you create an event source connection in a component, it isn't going to just close because you unmounted that component. It will live on. So also make sure you close the connection there if you unmount a component. There's also no guarantee that the browser isn't going to leave that stream hanging on the server side. So gracefully closing the connection will free up your resources immediately, as well as cutting the noise out of your monitoring systems. So Linux is a setting limiting the number of open files. And why does this matter to us? So everything in Linux is represented as a file, including open connections. On some flavors of Linux, the default can be as low as 1024. So that's going to cause you to hit the file limit and not be able to accept connections very quickly. And as a final reminder, that categorically did not happen to us. But about security, so expire your JWT tokens. When you're generating it, do not let it live forever. Because if you do, and it leaks, an attacker could subscribe to and listen to private updates from your hub forevermore, or at least until you change the signing key. And we all know how good engineers are at rotating keys and secrets. There was a nice update in version 0.14 that dropped last week. So now when that token expires, the hub will automatically disconnect the user. And previously, it would only just refuse a new subscription. A bit on resiliency. So the open source hub only supports a single node. If you need high availability, and are managed in a licensed version of the hub available, and they support several other transports that allow for fan-out, like Redis, Kafka, and there's some others. We use Redis, as it was already part of our stack for caching. There's also several other implementations of the hub that third parties have written. I can't speak to what they're like personally, but there's implementations in Python, Node, PHP available on GitHub, and the last two support clustering via Redis. The official implementation is written in Go, and without having benchmarked any of them, I imagine it's likely to be much, much faster. I've also said roll your own transport, but actually don't do that. One of the traps in software development is spending time building things that aren't your core business when you should be focusing on what actually makes your product unique. So actually don't do that. Time for some case studies. COP26 is the UN's climate change conference that came to Glasgow last year, my home city and where Raven is based, and it took over the entire city for around a month. Raven was procured by the UK government's Cabinet Office as the event's incident management system. So COP was a global event of critical importance. World leaders from around the globe attended, along with royalty, climate activists, heads of state, the likes of Jeff Bezos, Bill Gates, Leonardo DiCaprio and other celebrities. It was watched by a global audience. A huge event that took years of planning. Use of the system extended through government departments, the UN, all emergency services, local government, NHS, which is our National Health Service, transport organisations, private security, and on and on. In total, there were over 30 different agents with 1,000 users on the system concurrently. Around the city, there were 7 different command centres housing all these agencies, with the system providing shared situational awareness to all agencies in real time. Climate change is one of the key challenges facing the world today, and we saw thousands of people take to the streets and protest. These protests, alongside transport disruption, VIP movements, city disruption, people management, all had to be logged, allowing notification and escalation to those that needed to know, in order to respond to the ever-changing landscape as things change from minute to minute across the city, and ensure that the conference ran smoothly. Ultimately, despite all the enormous challenges, COP26 ran relatively smoothly. UEFA Euro 2020, this is where it gets serious. So there's venues in 11 cities across Europe, multiple matches on any given day, sometimes simultaneously. Raven was a direct link from the host city and the stadiums into UEFA headquarters in Nyon in Switzerland. There were many critical incidents throughout the tournament that warranted immediate response. So in Germany, we saw a Greenpeace protester paraglide into the stadium, strike spectators in the stand, and cause several serious injuries. In England, at the challenging scenes at the final in Wembley, as many as 2,000 fans violently broke into the event, causing chaos, creating crushing risks as they surged through enclosed spaces. Security were holding back another 6,000 people outside. And in Denmark, who can forget the terrible scenes involving Christian Eriksen? He went into cardiac arrest on the pitch and was given life-saving treatment. So why am I highlighting these events? In critical events like these, time matters. As I highlighted earlier in the talk, 30 seconds spent polling is too long to wait when somebody's life is at risk. The response to events like these needs to be immediate and coordinated. The right people have to be informed in order to make decisions, carry out actions in responding to the problem at hand. It goes way beyond providing a great user experience. Without real-time technologies, our system simply wouldn't be as effective. Threats to events go way beyond what I've highlighted in our case study. We've seen attacks at events here in France, at Nice and the Bataclan. In England, there's a bombing at Manchester Arena. At inquests, we've heard about the failings, slow and uncoordinated responses. Now, Truth is, no software or systems can foolproof against threats that surround us. But we can do a lot about many of these failings to prevent, mitigate, and respond better to these threats. And we can certainly do something about slow and uncoordinated responses, which is exactly what Mercure's real-time capabilities have helped us to do as one piece of this puzzle, as we've built an industry-leading system. For us, that's been the real-world impact of using this technology. You'll have seen some of the use cases where real-time can enhance your app and some of Mercure's unique features, like gather and missed events and the Presence API that go beyond streaming events now and offer new opportunities to make your own apps even greater. I spoke at the start about boring technologies. When choosing new technologies, you've got to evaluate if the benefits that technology is going to bring is worth the cost and the learning curve and the unknowns that lie in wait. Like everything in software engineering, there's a trade-off to be made. Whenever you gain something, you lose something else. It's probably pretty obvious by now that I think this particular decision has been a success. And hopefully today, we've helped document some of the unknowns that definitely didn't happen to us, that lie in wait, and played a part in making Mercure more well understood. Thank you. Seriously, thanks for listening. I hope it's been valuable. That was my first ever conference talk. Yesterday, after Maureen's talk on imposter syndrome, I had a question, which was, what if you've been invited to give a conference, to give a talk, but you're terrified nobody's interested in coming? So really, thanks for coming.